All right, AP Chemistry, this is the Day 50 assignment, the answers video to that. So it's more on rate mechanisms. This is a somewhat lengthy answers video, but a very important one. It really gets to the deep type of issues that they can ask you on the AP exam. So let's go ahead and get started. I may break this into several different parts, this answers video. So what is a rate mechanism? A rate mechanism, I want you to actually go back to the video and get the definitions that I have in the lecture video. But in short, a rate mechanism is the series of steps, of reactions that take place to get from the reactants at the beginning to the products at the end. This doesn't usually just happen in one single step where reactants automatically just quickly turn into products. There's usually several steps in between, and so that's the rate mechanism, is how is that done. It's nothing that you're ever expected to figure out. It's just something that's done experimentally by professional chemists to determine this. What is an elementary reaction? That is one of those reactions that leads from the reactants to the products. So there could be two, there could be three. Generally, the problems you'll be dealing with, there won't be more than three steps, three elementary reactions leading that produce the overall reaction that you're studying. What is an intermediate? An intermediate is a compound that's produced by one of the elementary steps and then consumed by a later elementary step. So it never appears in the initial reactants and it never appears in the final products. It's made in the middle of the reaction and it's consumed in the middle of the reaction. That's called an intermediate. What is a catalyst? It's almost the opposite of an intermediate. In general, it speeds up a reaction, but you'll see it at the beginning on the reactant side of the reaction, and then it also appears again on the product side of the reaction. So it appears both at the beginning and the end. And it's designed in one of several ways to speed up the rate of the reaction. Okay, so now we're going to go ahead and answer questions from your textbook, from chapter 14 of your textbook. I've transcribed them here for this assignment. I probably won't do that in the future. I'll just give you the numbers, and there will be a copy of the textbook for you to use in class, as well as the one that you have checked out that's at home. Okay? All right, so let's go ahead and get started with 14.25. So the decomposition of N2O5 proceeds as follows. And there it is right there. It says the rate law is first order in N2O5 at 64 degrees, the rate constant, and they give you that number right there. And a first order rate constant is always 1 over S. Okay, so that's the way you can express 1 over S. Write the rate law for the reaction. So the rate law only involves the products. So it's going to simply be, I said products, I meant to say reactants. Okay, and there we have it. It says it's first order, so therefore that exponent is 1, so we know the exponent. We don't have to write it, but I'll go ahead and do it right there. So that would be the rate law. B, what is the rate of the reaction when N2O5 is 0.0240 molar? Okay, so you just simply plug that number in. Okay, and I'm going to go ahead and omit units of measure because rate is always molar per second, molarity per second. So just to keep it from being as cluttered, I'm going to go ahead and just write it like this, like a math equation. Okay, and remember, when you have a scientific notation and a non-scientific notation, you just treat this like a coefficient. So you multiply this with the coefficient. And so that's going to give us 4.82 times 0.024, and that gives us 0.1156. We'll call it 0.116. We're going to adjust the decimal. We make this one bigger, so we make this one smaller. So it's going to become and it's molar per second. Rate is always molar per second. Okay, so there's the answer to that. What happens to the rate when the concentration of N2O5 is doubled to 0.48? So in a first order reaction, when the concentration is doubled, then the rate is doubled. If the concentration were tripled, then the rate would be tripled. That's the way it is. You can just simply see here. If you change that up there to 0.48, then it would have doubled. It would have doubled this number down here. Okay, 14.36. For a second order reaction, what quantity when graph versus time will yield a straight line? So you should have these memorized for 0, first, and second. So let's do all three of them just to reinforce it. For a zero order or zeroth order reaction, when you graph the concentration versus time, you get a negatively sloping straight line. That's 0. For first order, you also get a negatively sloping straight line when you graph the natural log of the concentration versus time. And to answer the question for a second order, it's when you get a positively sloping straight line when you graph the reciprocal of the concentration versus time. So that's the answer to that question, but you should have all three of these memorized. Okay, how do the half-lives of first order and second order reactions differ? Okay, so first order half-lives occur over equal time intervals and do not depend on concentration. Second order half-lives occur over different time intervals and are a function of concentration. So you notice that in the half-life for first order, nowhere is concentration of the reactant listed. It's simply this fixed number, 0.693, you don't have to understand why it is that number, over the rate constant, which is constant. So it's going to be a constant time interval. Second order, the half-life is 1 over the rate constant, but it's times the initial concentration. So that makes a difference. So the first order one is the one you should really understand what it looks like, and it's this. So I'll try to draw it as best I can freehand. But if I come down here, and let's say this is 100 right here. And it happens at a certain amount of time, then it will be cut in half to 50 in, let's just say, 1 minute. And let's say that's 50. Then 50 will be cut in half to 25 in another 1 minute. So the time intervals for first order are equal. You constantly cut it in half, whatever it is. So here it's 100, you cut that in half to 50. Here it's 50, you cut that in half to 25. If 25 would be cut in half to 12 and a half, each of those would take the same time interval of 1 minute. That's true only of a first order reaction. Second order is not quite as neat. It depends on the concentration at the beginning of each time interval, and so it's going to be constantly changing. Okay, so let's move on. 1441. So it says this reaction is first order, so that's a key. Okay, so you know what's going to create a straight line is if you take the natural log of the rate. It's going to give you a straight line. Using the following kinetic data, determine the magnitude of the first order rate constant. Okay, so since this is first order, now we're dealing with pressure, but it's exactly the same as concentration, as the square brackets, okay? We don't see pressure in the problems nearly as much, but it's treated exactly the same way. So what it's saying is that if we take the natural log of its first order of these numbers, it should give us a straight line. And if we can then find the slope of that straight line, that will tell us the rate constant. Okay, so we're going to take the difference of these two, take the natural log of each of these. So I'm going to write that right over here. So the ln of the pressure. Okay, and I'll just do those very quickly. I'm just show you one of them, the very first one. Okay, so natural log of 1, close parenthesis, gives us 0. Natural log of 0.947 gives us negative 0.054. We'll just round it there. Natural log of 0.895 is going to give us okay, now we're going to take differences. So we'll just subtract these two. So the difference here is so you can see, just with one little exception there, everything's about 0.054. That one's a little bit off, but that'll happen in the real world. It won't be exact. So that means when you take the natural log, you get a straight line. All the differences are the same. All the differences here are the same. That means you're going to get a straight line. So the way to know the slope of that straight line is pick any two of these points. Okay, so because this is a straight line, I'll pick these two down here. So the y-intercept is going to be, or the slope, the y component I should say, is going to be, I'm doing a minus negative here. So that's going to give me negative 0.219 minus negative 165. So that just becomes plus 0.165. Okay, and that gives us what we already figured out over the difference here is 10,000. I think that's a typo. 10,000 minus 7,500. It's going to be 2,500. And if we just divide that by 2,500, that is the 0.054, we get negative, and we're going to call it 2.16 times 10 to the minus 5. And since it's first order, it's 1 over seconds, or seconds to the negative 1. So that is the slope, and that is the rate constant. Okay, the rate constant is the positive part. The slope is negative because it just is. That's the way it is with the first order, but the actual rate constant is the positive portion. 2.16 times 10 to the negative 5, 1 over seconds. Okay, let's move on to 1453. Okay, so base number 1453, based on their activation energies and energy changes, and assuming that all collision factors are the same, which of the following reactions would be fastest and which would be slowest? Explain your answer. Okay, so these are on the next page. So we'll come over here. Okay, we're just going to sketch out an energy diagram for each of these. Okay. All right, so it just has to be just a little sketch here. So energy is on this axis and time is on this axis. And remember what the energy diagram looks like. It's going to start here with some reactance. We'll just call it RE. It's going to go up and then it's going to come down. Now, if the change in energy is negative, that means it's exothermic, so it's going to come down to a lower energy than it started right there. And this is products. Okay. So what it's saying is that the difference between the reactants and products, this distance right here, is negative 25. Okay. Kilojoules per mole. Okay. That really has nothing to do with the speed of the reaction. So this is kind of extraneous or superfluous information here. The big thing in determining the speed of the reaction is going to be the activation energy. And remember, that's the additional energy. Reactants already have some energy. So it's the energy you have to get them to get up over this mountain. That's called the activation energy, EA. Okay? So for the first one, it's negative 25. It goes from here down 25 to there. And the activation energy is 45. And it's kilojoules. Okay, let's draw it again for this one. Okay, so again, we'll say we start at the same place. Now this has an activation energy of 35. It's not as high as this one, so we're going to draw it a little lower. And then it doesn't give off as much energy. It doesn't go down quite as low, so it's going to go down to about right here. Okay, so this distance from here to here is negative 10 kilojoules. And this distance, which is the activation energy, is 35 kilojoules. That right there. All right, and finally the last one. These are both exothermic because they end up at a lower energy. That means energy, delta H, was negative. It had to go out. Boom, it had to go out of that. Negative delta H for this one. Energy had to go out like that. Now this one is positive delta E, so we're going to start at about the same place. Now it has a really high activation energy, so we're going to go way up here, and it's going to come down and end up at positive 10. So this distance is positive 10 kilojoules. The fact that it has a high activation energy has nothing to do with this being positive 10. And this is endothermic, so these two are exo, and this one is endo. Heat had to go into it. It ended up with more heat than it gave off. So it was a positive 10. Now the activation energy is this, and that's 55 kilojoules. So when you want to know which one is the fastest, it's going to be the one with the lowest activation energy. So this one is going to be the lowest. Where it ends up at the end has nothing to do with how fast the reaction is going to go. Or whether it's endothermic or exothermic has nothing to do with how fast. Remember what K depends on. It depends on temperature. Okay, well, we don't have any information, so we assume the temperature is all the same. It depends on activation energy, and it depends on the frequency factor, and we don't have. It said back there that the reactions, all collision factors are the same. Okay, that would mean temperature and frequency factor. Okay, remember our formula back there was A E to the minus activation energy over gas constant times temperature. Okay, so you're saying that these two are the same, the frequency factor and the temperature. So EA is the only thing that differs. So this one's going to be the lowest because the fastest because it has the lowest activation energy. This one's going to be the let me change that. I'm sorry. That I should have fastest. And this one is going to be the slowest. It had the lowest activation energy is what I meant, but it's the fastest reaction because of that. This one's the slowest because it has the highest activation energy, and this one is in between. So that's the answer to that question. Okay, we now move on to problem 1457. This might be the most difficult problem, so you have to refer back to the video. And it's really just the math that makes it difficult. You have to kind of, spot what you're trying to do here. So you're given an equation. We measured at several temperatures the following. That should be data collected. So you have temperature in centigrade, and you have a rate constant, and it's 1 over molar seconds, which implies that it's a second order reaction, because of those units of measure are uniquely for second order, but that doesn't really matter in this problem. And then it says use these data to graph natural log of K. So we have K, so we're going to calculate natural log of K. That's one thing we're going to do in this problem. Versus 1 over T. So we have T here, so we're going to calculate 1 over T. Okay, so what formula do we use? Well, I'm going to click on over to your lecture video. Okay, right here. And what we see here is we have this formula. It's on at about 16 minutes and 15 seconds into the lecture video. And there's the Arrhenius equation, which relates the rate constant with the frequency factor, the activation energy, the temperature, and the gas constant. And what you can do is, using math, is you can convert it to this equation. And again, why do we use natural logs or logs in general? It's to convert curved lines, which this equation is, into a straight line. So you see this has y equals mx plus b. That's just integrated math 1 formula for a straight line. So it has a slope, and the slope of this line is negative EA over r. And the x, which is the independent variable, is 1 over t. And the y-intercept b is natural log of a. So the dependent variable is natural log of k. The independent variable, which would be x in a math equation, would be 1 over t. All right, so we're going to write that formula down. Now, how do you get from this equation to this? It's too much information for right now. I'll leave that alone. If you want to see me derive that, get from here to here, you can do it using these principles of logarithms, which are on your reference sheet, your units of measurement reference sheet in your packet. Using these principles, you can do it, but I'm not going to do it here. So let's go on back and let's get to the problem. So the first thing I'm going to do is write down that equation, and it looks like this. Okay, there's the equation. So there's the y, that's the dependent variable. There's the slope. Okay, that's what we're interested in here, because it's asking us to figure out what EA is. And there's the independent variable, 1 over t, and natural log of a. Okay, so what we're going to do is, first we need to convert these temperatures to Kelvin. So 273 plus 15 is 288. And all the rest of these you just add 273 to get to Kelvin. So this is the Kelvin temperature. You need to be in Kelvin because this rate constant here is in Kelvin, not in centigrade. Okay, and so there's the Kelvin temperatures. Now I'm going to pause the video here just briefly, and I'm going to calculate the 1 over t for each of these. I'm simply going to take the reciprocal here. So I'll go ahead and do that on one of them. So 288 and I hit the x to the minus 1, that's reciprocal, and that gives me this. And I should really write this in scientific notation, but I'll go ahead and just write it out as a decimal number. Now let me calculate one of these. I'm simply going to take the natural log, move that to right here, and it's going to be ln right there, and we're going to put in okay, and that's going to give us negative 2.95. Okay, and that's the way we'll do the rest of them, so I'll just pause and do all of those. Okay, so we continue. So this number is 1 over 298, this number is 1 over 308, so on. And these numbers are all the natural logs of these right here. So now what we're doing is we know that this is a straight line because it has a straight line form of an equation. So if we want the slope intercept, this is going to be the, in y equals mx plus b form, this is the y and this is the x. So this over here is going to be the numerator of the slope. So what we're trying to do, let's just go ahead and solve this. We're going to forget about ln right now. We don't care about that. So we're going to solve this. So to get the slope, it's ln k over 1 over t. And that's going to equal this. And that will be the slope of the line. So we're going to take these numbers, they're going to take the difference between the biggest and the smallest here. So that's going to be negative 2.95 minus negative 1.1, but so I'm going to call that plus 1.1. You're subtracting a negative. And that gives you negative 1.85. That's the difference between these two right here. Now we're going to do the same between these two right here. All right, and we're going to subtract this one minus this one. And this is not chemistry. This is integrated math 1. Okay, this is doing slope-intercept form of lines. It's just the numbers are a little more complicated than what you had in math class. Okay, and it's point 0.0033. Okay, so this one on top, this one on bottom right here. This one on top, this one on bottom. So what we get is this. And I'll go ahead and do that. Negative 1.85 divided by and that gives us 5.61 or negative 5,606. I'm not going to do scientific notation here. It'd probably be a good idea. Not worried about units of measure. It's simply going to equal this. Now this is a constant, and we know that this constant is 8.31. Okay, so if we want to know EA, this number right here, that's what the question's asking us for. I'll come over here and I'll write it out. So negative EA over 8.31. That's the gas constant that we use in this problem, not the 0.08211. But this one is joules over moles Kelvin. Okay, equals this. So what we're going to do is multiply top and bottom. Okay, so all I did was multiply top of both sides by 8.31, so these cancel. And the negative signs you can turn into a positive sign here. They're both going to cancel out. Okay, so the EA is going to equal these two numbers multiplied together. And that gives us 46,586. And that is going to be kilojoules per mole of activation energy. That's the activation energy. And that's the final answer. Okay? The book gets a slightly different number. It gets 47,000, but that's close enough. Okay? We're rounding numbers here. I didn't carry these out to the full number of decimal places. So I'm good with that answer right there. So it's kind of a messy problem. Again, it involves this formula that you get at minute number 16:15 of the lecture video. And it's just a matter of manipulating the variables to get 1 over k and natural log of k, excuse me, 1 over time, this right here, and natural log of k, this right here. Then you solve for this. You know what R is, you can figure out what EA is, okay? So I'm going to leave one like this for you to do entirely on your own. I'll do it in class or in tutoring with you, and that's going to be the next problem, which is going to be 1458. I'm going to conclude this video right here. It's getting, I don't want the videos to go on too long, and I'll pick up the rest of the problems on the next video.